You think we are small? You have no idea. What you're about to discover will shatter every assumption you have about scale, size, and your place in existence. The universe is so incomprehensibly vast that your brain literally cannot process its true scale. But here's the beautiful part. Understanding just how tiny we are might be the most profound realization you'll ever have. And here's a question for you. If you could choose to instantly understand one mystery of the universe, what would it be? Let me know in the comments. I will pin the most creative answer. Now let us begin. If you could drive to the moon in your car at highway speed, around 60 miles per hour, it would take you roughly 167 days of non-stop driving to get there. That's more than 5 months, just sitting in your car without sleeping, without stopping for food or gas. And that's just to reach the moon, something you can see with your naked eye on a clear night. The astronauts who went there in the 1960s and 70s took about 3 days to make the journey using the most powerful rockets ever built at that time. Think about that for a moment. The moon looks so close in the sky, like you could almost reach up and grab it. But it would take you 5 months of continuous driving to actually reach it. Your brain sees the moon as nearby because you can see it clearly. But the reality is vastly different. This is where your intuition starts breaking down. Evolution didn't prepare us to think about distances like this. For millions of years, our ancestors only needed to understand distances they could walk in a day, maybe a week. Anything beyond that was simply far away, and the exact distance didn't matter for survival. But we're just getting started. Let's travel a bit further out. The sun, that blazing ball of nuclear fusion that gives us life, sits 93 million miles away from Earth. Scientists call this distance one astronomical unit, or AU for short. It's a convenient measuring stick for distances within our solar system. Light from the sun, traveling at the fastest speed possible in our universe, takes about 8 minutes and 20 seconds to reach your eyes. When you look at the sun, please don't actually stare directly at it. You're seeing it as it was 8 minutes ago. You're literally looking into the past. If you tried to drive to the sun at 60 miles per hour, it would take you 177 years. That's longer than any human has ever lived. You'd need multiple generations of people to complete that road trip. Your great-great-great-grandchildren might finally arrive, assuming someone figured out how to build a car that could survive the journey through the vacuum of space and not melt when getting close to a ball of plasma that's 10,000 degrees Fahrenheit on its surface. Now here's something that might surprise you. All the planets you learned about in school, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, they all orbit within a relatively tiny bubble around the Sun. Neptune, the furthest official planet in our solar system, orbits at about 30 AU from the Sun. That's roughly 2.8 billion miles away. Light from the Sun takes about 4 hours to reach Neptune. At our highway driving speed, it would take you 5,300 years to drive there. That's longer than all of recorded human history. But here's the thing that really messes with your mind. Neptune isn't even close to being at the edge of our solar system. Not even remotely close. Beyond Neptune lies a region called the Kuiper Belt, a donut-shaped collection of icy objects and dwarf planets like Pluto. That extends out to about 50 AU. Beyond that lies the scattered disk, reaching out to perhaps 1,000 AU. And beyond that, the Oort cloud, a theoretical shell of icy objects that surrounds our entire solar system. Scientists believe the Oort cloud might extend anywhere from 5,000 to 100,000 AU from the Sun. That's nearly 2 light years away. A light year, by the way, is the distance light travels in 1 year. Light moves at 671 million miles per hour. In 1 year, it covers about 5.9 trillion miles. And the Oort cloud might extend 2 light years out. Try to imagine that distance. You can't, really. Nobody can. Your brain simply isn't equipped to visualize 5.9 trillion miles, let alone twice that amount. If you're enjoying this journey through the cosmos and feeling your mind expand with each new scale we explore, hit that subscribe button and give this video a thumbs up. It helps more people discover these incredible cosmic truths, and it means the world to me as I build this channel. Now here's a wild thought. If you could shrink the sun down to the size of a ping pong ball, about 1.5 inches across, and you placed it on the goal line of a football field, where would Earth be? You might think somewhere near the 50-yard line, maybe in the end zone at the other end of the field. Nope. Earth would be about 8 feet away, roughly the size of a grain of sand. Jupiter, the largest planet in our solar system, would be about 85 feet away, about the size of a small pea. And Neptune? That would be sitting about 240 feet away, nearly the length of an entire football field, as a slightly smaller grain of sand. That's our solar system at this scale, the Sun as a ping pong ball, and all the planets would fit within about the length of a football field, most of them so small you'd need a magnifying glass to see them. But here's where it gets absolutely insane. The Oort cloud, that distant shell of icy debris at the edge of our solar system, would extend outward for about 10 miles in our ping-pong ball model. 10 miles of mostly empty space with a few tiny ice chunks scattered throughout. That's our solar system, and this is just one star system, one tiny neighborhood in a cosmic city so vast that it defies all comprehension. Now let's talk about our nearest stellar neighbor. The closest star to our Sun is called Proxima Centauri, part of the Alpha Centauri triple star system. It sits 4.2 light-years away. Remember, 1 light-year is almost 6 trillion miles, so Proxima Centauri is roughly 25 trillion miles from us. If you tried driving there at 60 miles per hour, it would take you 47 million years. Modern humans, Homo sapiens, have only existed for about 300,000 years. So you'd need to start driving long before humans even evolved, back when our ancestors were still primitive apes, and you still wouldn't be there yet. Light from Proxima Centauri takes 4.2 years to reach Earth. When you look up at that star through a telescope, you're seeing it as it was 4 years ago. If aliens living on a planet orbiting Proxima Centauri were looking at Earth right now through a powerful telescope, they'd be seeing us as we were in 2022. They'd have no idea what's happening on Earth right now. The information simply hasn't reached them yet because of the finite speed of light. Even light, the fastest thing in the universe, takes years to cross these distances. In our ping-pong ball model, where the Sun is 1.5 inches across and the whole solar system fits within 10 miles, how far away would Proxima Centauri be? Take a guess. 100 miles, 500 miles, try 2,000 miles. If the Sun were a ping-pong ball in New York City, Proxima Centauri would be another ping-pong ball in New Mexico. That's the distance between stars. Mostly empty space with occasional balls of burning gas scattered throughout, separated by distances so enormous that light itself takes years to cross them. And Proxima Centauri is our closest neighbor. There are roughly 400 billion stars in our Milky Way galaxy, and they're all separated by distances like this, or even greater. Most stars are several light-years apart from their nearest neighbors. Some are dozens or hundreds of light-years from the next closest star. The galaxy is mostly empty space with tiny islands of matter floating in an ocean of darkness. Let's zoom out even further. Our Milky Way galaxy is a spiral galaxy shaped kind of like a giant pinwheel or a fried egg with spiral arms. It's about 100,000 light-years across. That means light, traveling at 671 million miles per hour, takes 100,000 years to cross from one edge of our galaxy to the other. If you started at one edge of the Milky Way when the last ice age was ending and humans were just beginning to develop agriculture, and you traveled at the speed of light, you'd just now be arriving at the opposite edge. Our entire recorded history, every empire that ever rose and fell, Every war ever fought, every discovery ever made, all of it would happen during just a tiny fraction of the time it takes light to cross our galaxy. Our Sun sits about 26,000 light-years from the center of the Milky Way. We're out in the suburbs, you might say, in a spiral arm called the Orion Arm or Orion Spur. We orbit around the galactic center once every 225 million years. The last time our solar system was in this exact position in its galactic orbit, dinosaurs were just starting to appear on Earth. Think about that. The galaxy rotates so slowly that it takes longer than the entire reign of the dinosaurs for our Sun to complete one single lap around the center. At the heart of our galaxy sits a supermassive black hole called Sagittarius A star. This monster has a mass of about 4 million times that of our Sun, all compressed into a region smaller than Mercury's orbit. We know it's there because we can see stars orbiting around it at incredible speeds. In 2020, scientists released the first actual image of Sagittarius A star, or rather, the glowing ring of matter surrounding it, since black holes themselves don't emit light. The Event Horizon Telescope, a network of radio telescopes spread across the entire planet working together, captured this image by essentially turning the whole Earth into one giant telescope. That photo showed us the heart of our own galaxy, something our ancestors could never have imagined existed. Speaking of things our ancestors couldn't imagine, just recently in January 2026, scientists using data from the James Webb Space Telescope created the most detailed map of dark matter ever made. They observed nearly 800,000 galaxies over 255 hours of observation time. Dark matter is this mysterious substance that doesn't emit, absorb, or reflect light, but we know it's there because of its gravitational effects on visible matter. It's essentially invisible glue holding galaxies together. This new map is helping scientists understand how dark matter shapes the large-scale structure of the universe. If you want to dive deeper into how Webb is revolutionizing our understanding of cosmic scale and revealing things we never thought possible, check out my video called James Webb Just Revealed the True Scale of the Universe. It goes into even more mind-blowing detail about what we're discovering at the edge of observable reality. The link is in the description and on the card above, but let's get back to scale. So we've established that our galaxy is 100,000 light-years across, right? Now brace yourself. The Milky Way isn't alone. It's part of a small group of galaxies called the Local Group, which contains about 80 galaxies total. The biggest member is the Andromeda Galaxy, also called Messier 31 or M31. Andromeda is slightly larger than the Milky Way and sits about 2.5 million light-years away from us. 2.5 million light-years, let that sink in. The light you see from Andromeda, which you can actually spot with your naked eye on a dark night if you know where to look, left that galaxy 2.5 million years ago. Back when that light began its journey toward Earth, humans didn't exist yet. Our evolutionary ancestors were barely using stone tools. Homo erectus was just starting to spread across Africa. Every step forward in human evolution, the discovery of fire, the invention of language, the development of art and culture, the rise of civilization, all of it happened while that light was traveling through space toward your eyes. And here's something fascinating that scientists discovered just in 2025. For decades, astronomers thought the Milky Way and Andromeda were definitely going to collide in about 4 billion years. But new measurements from the Gaia spacecraft, which is precisely mapping the positions and movements of billions of stars, suggest that the collision might not be certain after all. There's a chance the two galaxies might just have a close encounter and swing past each other instead. Either way, when and if they do eventually merge, it'll create a new elliptical galaxy that some scientists have nicknamed Milkomeda. By that time, our sun will be nearing the end of its life anyway, so humanity, if we still exist in any form, will have much bigger problems to deal with. The local group spans about 10 million light-years across, but it's just a tiny neighborhood in a much larger structure. The local group is part of the Virgo supercluster, also called the local supercluster, which contains at least 100 galaxy groups and clusters. The whole thing stretches about 110 million light-years across and contains approximately 47,000 galaxies. 47,000 entire galaxies, each containing hundreds of billions of stars, each of those stars potentially having planets orbiting around them. The numbers become so large they lose all meaning. Your brain just can't hold on to quantities that enormous. But we're still not done zooming out. In 2014, scientists discovered that our Virgo supercluster is actually just one lobe of an even larger structure called the Laniakea supercluster. Laniakea is a Hawaiian word meaning immeasurable heaven, which is pretty appropriate. This cosmic titan contains about 100,000 galaxies and spans 520 million light-years across. All of these galaxies, including our own Milky Way, are being pulled toward a region called the Great Attractor, a gravitational anomaly located roughly 150 million light-years away. We can't see the Great Attractor directly because it's hidden behind the plane of our own galaxy, but we can detect its influence on the motion of thousands of galaxies. Now here's where things get truly bizarre. Beyond Laniakea, there are countless other superclusters scattered throughout the observable universe. The Shapley supercluster, the Hercules supercluster, the Coma supercluster, each one containing tens of thousands of galaxies. These superclusters aren't randomly distributed either. They form patterns, vast filaments and sheets of galaxies separated by enormous voids where almost nothing exists. Scientists call this the cosmic web, and it's one of the most beautiful large-scale structures in nature. Imagine a sponge. The solid parts of the sponge represent the filaments where galaxies cluster together, and the holes represent the voids, vast empty regions of space containing very few galaxies. The cosmic web looks eerily similar to the structure of neurons in your brain or the structure of mycelium, the underground fungal networks that connect trees in a forest. There's something deeply profound about how patterns repeat at vastly different scales throughout nature, from the microscopic to the cosmic. These cosmic voids are unimaginably empty. The Buddha's void, discovered in 1987, is a roughly spherical region of space about 330 million light-years in diameter that contains only about 60 galaxies. That might sound like a lot until you realize that a typical region of space that size would contain around 10,000 galaxies. It's so empty that if you lived in a galaxy in the middle of the Buddha's void, you might not even know other galaxies existed. Your night sky would be almost completely black, with perhaps just a handful of faint smudges visible through the most powerful telescopes. Scientists aren't entirely sure why these voids exist. The leading theory involves dark energy, that mysterious force causing the universe to expand at an accelerating rate. In the early universe, tiny quantum fluctuations got amplified as space expanded. Regions that were slightly denser attracted more matter and became the filaments and clusters we see today. Regions that were slightly less dense had their matter pulled away toward those denser regions, creating the voids. Over billions of years, this process created the cosmic web structure we observe. Speaking of dark energy, this is another mind-bending piece of the cosmic puzzle. In 2025, astronomers analyzing data from various telescopes found evidence that dark energy might actually be weakening over time. For context, dark energy makes up about 68% of all the energy in the universe. It's the mysterious force pushing space itself to expand faster and faster. If it's weakening, that could dramatically change our predictions about the ultimate fate of the universe. Will expansion continue forever, leading to a cold, dark, eternally expanding cosmos? Or might expansion slow down, stop, or even reverse? We simply don't know yet, and that uncertainty is both terrifying and exhilarating. Think about this for a moment. We've spent billions of dollars building telescopes and sending spacecraft across the solar system. We've trained thousands of brilliant scientists who have dedicated their entire lives to studying the cosmos. And after all that effort, we've discovered that we only understand about 5% of what the universe is made of. The other 95% is dark matter and dark energy, substances we can't see, can't touch, and barely understand. It's like being given a jigsaw puzzle where 95% of the pieces are invisible. You can see the rough outline of the picture, but most of it remains a complete mystery. Now let's talk about the observable universe. This is the region of space from which light has had time to reach us since the Big Bang. The universe is approximately 13.8 billion years old. You might think that means the observable universe is 13.8 billion light-years in radius, but you'd be wrong. Remember, space itself is expanding. While light was traveling toward us from distant galaxies, those galaxies were being carried away from us by the expansion of space. When we account for this expansion, the observable universe has a radius of about 46.5 billion light-years. That means the observable universe is roughly 93 billion light-years across, 93 billion light-years. Your brain cannot comprehend this distance. It's impossible. Remember, 1 light-year is almost 6 trillion miles. Multiply that by 93 billion. You get a number with 23 digits, 558 septillion miles. That's the diameter of the observable universe. If you printed that distance in miles and used a normal-sized font, the number alone would stretch across an entire page. The observable universe contains an estimated 2 trillion galaxies. That's 2,000 billion galaxies. Each galaxy contains anywhere from a few million to several trillion stars. Let's be conservative and say the average galaxy has 100 billion stars. That gives us 200 sextillion stars in the observable universe. That's a 2 followed by 23 zeros. There are more stars in the observable universe than grains of sand on all the beaches on Earth. In fact, there are probably more stars than all the grains of sand on Earth combined, including deserts and ocean floors. And every single one of those stars is potentially orbited by planets. In 2025, astronomers announced the discovery of several new exoplanets orbiting nearby stars. We now know of over 5,000 confirmed exoplanets, and statistical analysis suggests that nearly every star has at least one planet. Some estimates suggest there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of Sun-like stars just in our Milky Way galaxy alone. 40 billion potentially habitable worlds in our galaxy alone. Multiply that by 2 trillion galaxies and the numbers become so absurdly large they're meaningless. But here's the really wild part. The observable universe might not be the entire universe, it's just the part we can see. Beyond the observable universe, there could be much more, perhaps infinitely more. Light from regions beyond 46.5 billion light-years simply hasn't had time to reach us yet because the universe is only 13.8 billion years old. As time goes on, we'll be able to see slightly farther as light from more distant regions finally arrives. But because space is expanding, there are regions we will never be able to see, no matter how long we wait. Those regions are receding from us faster than light can travel through space. They exist beyond what scientists call the cosmic horizon. Is the universe infinite? We don't know. It could be. It could extend forever in all directions, containing an infinite number of galaxies, stars, and planets. Or it could be finite, but unbounded, like the surface of a sphere. If you walk in one direction on Earth's surface long enough, you'll eventually come back to where you started. The universe might work the same way, travel far enough in one direction, and you might eventually return to your starting point from the opposite direction, having circumnavigated the entire cosmos. Or the universe might have some other topology entirely that we haven't even imagined yet. The James Webb Space Telescope has been giving us unprecedented glimpses of the early universe. It can see farther back in time than any telescope before it, observing galaxies that formed just a few 100 million years after the Big Bang. Some of these early galaxies are surprisingly large and mature, challenging our theories about how quickly galaxies can form. In fact, discoveries from Webb are making scientists reconsider some fundamental ideas about the cosmic dawn, that period when the first stars and galaxies were forming. One fascinating possibility that's emerged from Webb's observations involves dark stars. These would be hypothetical stars powered not by nuclear fusion like normal stars, but by dark matter annihilation. If dark matter particles can collide and destroy each other, releasing energy, that energy could potentially power a star. Some researchers think certain objects Webb has observed might actually be dark stars rather than conventional galaxies. If confirmed, this would be revolutionary, giving us our first direct observation of dark matter doing something other than just exerting gravitational pull. But whether these objects are dark stars or just surprisingly mature early galaxies, one thing is clear. The universe was far more active and dynamic in its youth than we expected. Galaxies formed faster, grew larger more quickly, and began their cosmic dance earlier than our models predicted. Every new observation raises new questions. That's the beauty of science. Every answer leads to 10 more questions. Let's bring this back down to Earth for a moment, literally. You're sitting on a planet that's 8,000 miles in diameter. That planet orbits a star 93 million miles away. That star is one of 400 billion stars in a galaxy 100,000 light-years across. That galaxy is one of roughly 80 galaxies in the local group. The local group is part of the Virgo supercluster, which is part of the Laniakea supercluster, which is just one of millions of superclusters in the observable universe, which might itself be just a tiny fraction of the total universe. You are unimaginably small. A speck on a speck on a speck, floating in an ocean of darkness so vast that it makes the deepest parts of Earth's oceans look like a puddle. And yet, you're also unimaginably significant. You're made of atoms forged in the hearts of dying stars. The carbon in your muscles, the calcium in your bones, the iron in your blood, all of it was created billions of years ago in stellar furnaces and scattered across space when those stars exploded. You are literally made of stardust. Every atom in your body has a cosmic origin story spanning billions of years, but it gets even better. You're not just made of star stuff, you're made of universe stuff. The hydrogen atoms in your body, the most abundant element in your composition, weren't forged in stars. They're even older than that. They were created in the first 3 minutes after the Big Bang, when the universe was a hot, dense soup of subatomic particles. Those hydrogen atoms in your cells are 13.8 billion years old. You're walking around with pieces of the primordial universe inside you. Think about what that means. The atoms that make up your body have been on an incredible journey. They started in the Big Bang, drifted through space for millions of years, eventually got pulled into giant clouds of gas that collapsed to form stars. Inside those stars, some of them fused into heavier elements. When those stars died, they exploded, scattering those elements across light years of space. Those atoms drifted again, eventually becoming part of new clouds that formed new stars, including our Sun. They became part of the spinning disk of dust and gas around the young sun, gradually clumping together to form planets. They cycled through Earth's crust, oceans, and atmosphere for billions of years. They were part of ancient bacteria, trilobites in primordial seas, dinosaurs, early mammals, and eventually humans. The atoms in your left hand might have been part of different stars than the atoms in your right hand. You're an assembly of ancient cosmic travelers that have journeyed across space and time to come together briefly to form you. And when you die, those atoms will continue their journey. They'll become part of soil, plants, animals, and maybe someday, billions of years from now, they'll be part of stars again. You're not separate from the universe. You're a temporary pattern that the universe is making with itself. You're the universe experiencing itself, a way for the cosmos to know itself. Now let's talk about time, because understanding cosmic scale isn't just about distance, it's also about duration. The universe is 13.8 billion years old. That's an incomprehensibly long time, but let's try to put it in perspective. Imagine the entire history of the universe compressed into a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. For the first few months, nothing much happens except hydrogen and helium gas spreading out and cooling down. The first stars form around January 12th. The first galaxies begin taking shape by the end of January. Our Milky Way galaxy forms around February 16th. But our solar system doesn't appear until September 2nd, about 2/3 of the way through the cosmic year. Earth forms on September 6th. The first life appears on Earth, simple, single-celled organisms, around September 21st. For months after that, life remains microscopic. Complex multicellular life doesn't show up until mid-December. Dinosaurs appear on December 25th, Christmas Day, and go extinct on December 30th. All of human history, from the first anatomically modern humans until now, takes place in the last hour of December 31st. Agriculture was invented 11 minutes before midnight. The pyramids were built 6 minutes before midnight. Jesus lived 2 minutes before midnight. The Industrial Revolution happened 14 seconds ago. World War II ended 9 seconds ago. The internet was invented 3 seconds ago. Your entire life, every memory you have, everything you've ever experienced, is a fraction of a second in the cosmic calendar. If the universe were a person, humanity would be a thought that just crossed their mind. We've existed for such an incredibly brief moment that we're essentially brand new to the cosmos. And yet, in that brief moment, we've gone from banging rocks together to building space telescopes that can peer back to the dawn of time. We've gone from thinking the Earth was the center of everything to understanding our place in a universe containing trillions of galaxies. That's remarkable, but here's something that should really blow your mind. We're living in a very special time in cosmic history. Right now, the universe is just the right age for complex structures like galaxies, stars, and planets to exist. Go back too far, and the universe is too hot and chaotic for stable structures. Go forward too far into the future, and things get bleak. In about 100 billion years, all the galaxies outside our local group will have been carried so far away by cosmic expansion that they'll be beyond our cosmic horizon. Future astronomers won't be able to see them anymore. The night sky will contain only the handful of galaxies in our local group. Everything else will have disappeared beyond the observable universe. In about 1 trillion years, star formation will mostly cease. The universe will have used up most of its hydrogen gas the fuel stars need to form. The existing stars will gradually burn out and die. In 100 trillion years, all the stars will be gone. The universe will enter what's called the degenerate era, populated only by dead stellar remnants. White dwarfs, neutron stars, and black holes drifting through an ever-expanding darkness. In 10 to the power of 100 years, even the black holes will evaporate due to Hawking radiation. After that, the universe will be cold, dark, and essentially dead. No stars, no planets, no structure of any kind, just elementary particles spread across an incomprehensibly vast space, slowly drifting apart forever. That's the heat death of the universe, the most likely ultimate fate of everything based on our current understanding. Unless dark energy behaves differently than we think, or unless there's some mechanism we haven't discovered yet, that's where we're headed. But remember, that's trillions upon trillions of years in the future. For now, we live in what you might call the stelliferous era, the age of stars. We're alive during the time when the universe is lit up with billions of trillions of burning suns. We're here to witness the universe in its prime. But wait, it gets even stranger. Some physicists think our universe might not be alone. There's a theoretical framework called eternal inflation that suggests our Big Bang might not have been the only one. Space itself might be infinite, and Big Bangs might be happening all the time in different regions, each creating its own bubble universe with its own laws of physics. If this is true, then our observable universe, already 93 billion light-years across and containing 2 trillion galaxies, is just one bubble in an infinite cosmic foam. There could be infinitely many other universes forever beyond our reach, each with potentially different physical constants, different numbers of dimensions, maybe even different fundamental forces. In some of these hypothetical universes, the forces might be too strong or too weak for atoms to form. Others might have no stars because gravity works differently. Some might expand so fast they never form structures at all. Others might collapse back on themselves immediately. The vast majority of possible universes would be completely lifeless, unable to support any kind of complexity. We happen to exist in one of the rare universes where the constants are just right for stars, planets, and life. Some scientists call this the anthropic principle. We observe a universe compatible with life because we couldn't exist in any other type of universe to observe it. Is that a satisfying explanation? Not really. It raises more questions than it answers. Why do these laws of physics exist at all? Why is there something rather than nothing? These questions take us beyond the realm of science and into philosophy. Science can tell us how the universe works, but it struggles with the question of why the universe exists in the first place. Maybe there's no reason. Maybe existence is just a brute fact that doesn't require explanation. Or maybe there's a deeper answer waiting to be discovered. Here's another wild idea. Some physicists have proposed that we might be living in a simulation, a kind of cosmic computer program created by some advanced civilization. Before you dismiss this as science fiction, consider that we're already creating increasingly sophisticated simulations ourselves. Video games and virtual reality are becoming more realistic every year. If technology continues advancing, it's conceivable that future civilizations could create simulations so detailed that beings inside them would think they were real. If that's possible, then there could be far more simulated universes than real ones. Statistically speaking, you'd be more likely to exist in a simulation than in base reality. Now, I'm not saying we definitely live in a simulation. There's no hard evidence for it, and it's not a scientifically testable hypothesis at the moment. But it's a fascinating thought experiment that highlights just how strange and uncertain our understanding of reality becomes when we push our thinking to the extremes. The more we learn about the universe, the more we realize how much we don't know. Let's bring things back to something a bit more concrete. One of the ways scientists measure cosmic distances is through a technique called the cosmic distance ladder. It's a series of methods, each building on the previous one, allowing us to measure progressively farther distances. For nearby objects in our solar system, we can use radar. We bounce radio waves off planets and moons and measure how long it takes for the signal to return. That tells us exactly how far away they are. For stars within a few thousand light-years, we use parallax. As Earth orbits the Sun, nearby stars appear to shift positions slightly against the background of more distant stars. By measuring this shift, we can calculate the distance using simple geometry. The European Space Agency's Gaia spacecraft has been measuring the parallax of over 1 billion stars with unprecedented precision, creating the most detailed three-dimensional map of our galaxy ever made. For more distant objects, we use what are called standard candles. These are astronomical objects with known intrinsic brightness. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it must be. It's like seeing a candle in the distance. If you know it's a standard candle that emits a certain amount of light, the dimmer it appears, the farther away it must be. One of the most important standard candles is a type of exploding star called a Type Ia supernova. These happen when a white dwarf star in a binary system pulls matter from its companion until it reaches a critical mass, about 1.4 times the mass of our Sun. At that point, it explodes with a consistent brightness. No matter where in the universe a Type Ia supernova occurs, it reaches approximately the same peak luminosity. By observing these explosions in distant galaxies, astronomers can measure how far away those galaxies are. In the late 1990s, two teams of astronomers used Type Ia supernovae to make a discovery that shocked the scientific world. They expected to find that the expansion of the universe was slowing down due to gravity. Instead, they found that expansion was speeding up. This discovery led to the concept of dark energy and earned the researchers the Nobel Prize in Physics in 2011. It completely changed our understanding of the universe's fate. But measuring cosmic distances isn't easy, and there's an ongoing controversy in cosmology called the Hubble tension. When scientists measure the expansion rate of the universe using nearby observations, they get one number. When they calculate it using observations of the early universe from the cosmic microwave background, they get a different number. These measurements should agree, but they don't. Either there's something wrong with our measurements, or there's something fundamentally incomplete about our understanding of how the universe works. This is one of the biggest unsolved problems in cosmology right now. Another tool for understanding cosmic scale is the cosmic microwave background, or CMB. This is the oldest light in the universe, released about 380,000 years after the Big Bang. Before that moment, the universe was so hot and dense that light couldn't travel freely. It was like being inside a glowing fog. Photons would travel a tiny distance before colliding with an electron or proton. But as the universe expanded and cooled, it reached a temperature where electrons and protons could combine to form neutral hydrogen atoms. Suddenly the fog cleared and light could travel freely through space. That light has been traveling through the universe ever since, and we can still detect it today. It's been stretched by the expansion of space from visible light into microwaves, hence the name cosmic microwave background. When you look at the CMB, you're seeing the universe as it was 380,000 years after its birth. You're literally looking at baby pictures of the cosmos. The CMB is everywhere. If you could see in microwave frequencies, the entire sky would glow with this faint radiation. In fact, about 1% of the static you see on an old analog TV is actually CMB radiation. You've been looking at echoes of the Big Bang your whole life without realizing it. Scientists have created incredibly detailed maps of the CMB using satellites like WMAP and the Planck spacecraft. These maps show tiny variations in temperature, just a few millionths of a degree, across different regions of the early universe. Those tiny fluctuations were the seeds that grew into all the structure we see today. Slightly denser regions attracted more matter and eventually became galaxy clusters. Slightly less dense regions became voids. Everything in the present-day universe, every star, every galaxy, every planet, every person, can trace its origins back to quantum fluctuations in the first fraction of a second after the Big Bang. Think about that. The pattern of atoms that make up your body was determined by quantum randomness 13.8 billion years ago. If those quantum fluctuations had been even slightly different, the universe would have evolved differently. The Milky Way might not exist. The Sun might never have formed. Earth would never have come into being. You wouldn't be here. Your existence depends on a very specific sequence of events stretching back to the origin of everything. Now let's talk about something that really demonstrates the incomprehensible scale of the universe: light travel time. We mentioned this before, but let's dive deeper. When you look at anything, you're seeing it in the past. The light takes time to travel from the object to your eyes. When you look at your hand, you're seeing it as it was a few billionths of a second ago. When you look at someone across the room, you're seeing them as they were a few nanoseconds ago. These delays are so tiny they don't matter in everyday life. But as distances increase, the delays become significant. When astronauts on the moon talked to mission control in Houston, there was a noticeable delay. Radio signals, which travel at the speed of light, took about 1.3 seconds to travel from the moon to Earth, so there was a 2.6-second delay between asking a question and getting a response. During the Apollo missions, you can hear this delay in the recordings. It's subtle but definitely there. When we communicate with spacecraft on Mars, the delay is much longer. Depending on where Earth and Mars are in their orbits, the distance between them varies from about 34 million miles to 250 million miles. That means the signal delay ranges from about 3 minutes to 22 minutes. When the Mars rovers like Curiosity or Perseverance encounter a problem, they can't wait for instructions from Earth. By the time the problem report reaches Earth and engineers send back a solution, many minutes will have passed. The rovers have to be smart enough to handle problems on their own. The Voyager 1 spacecraft, launched in 1977, is now over 15 billion miles from Earth. That's about 163 times farther from the Sun than Earth is. Signals from Voyager 1 take about 22.5 hours to reach Earth. When scientists send a command to Voyager, they have to wait 45 hours to find out if it worked. That's almost 2 full days for a single back-and-forth communication. And Voyager 1, despite being the most distant human-made object, hasn't even left the solar system yet, not really. It crossed the heliopause, the boundary, where the solar wind gives way to interstellar space, back in 2012. But it's still nowhere near the Oort cloud, that distant shell of icy objects we talked about earlier. It won't reach the inner edge of the Oort cloud for another 300 years. It won't emerge from the outer edge for another 30,000 years. By that time, human civilization will be unrecognizably different, assuming we still exist at all. When you look at Proxima Centauri, the closest star, you're seeing it as it was 4.2 years ago. If aliens on a planet orbiting that star decided to send us a radio message right now, we wouldn't receive it until 2030. If we sent a reply immediately, they wouldn't get it until 2034. That's an 8-year delay for a simple back-and-forth conversation with our nearest stellar neighbors. When you look at stars 100 light-years away, you're seeing them as they were in the 1920s. The light reaching your eyes right now left those stars when people were listening to radio for entertainment, when the first talking motion pictures were just being invented before antibiotics were discovered. When you look at stars 1,000 light-years away, you're seeing them as they were in the year 1026 during the Middle Ages. Those stars might not even exist anymore. They could have exploded as supernovae centuries ago, but we won't know until the light from that explosion reaches us. When you look at a galaxy 1,000,000 light-years away, You're seeing it as it was when our early human ancestors were just starting to use fire. When you look at galaxies a billion light years away, you're seeing them as they were before complex life existed on Earth, when the most advanced organisms were simple, multicellular creatures in the oceans. When you look at the most distant galaxies we've ever observed, over 13 billion light years away, you're seeing them as they were when the universe itself was young, just a few 100 million years old. The universe is a time machine. Every time you look up at the night sky, you're looking into the past. The deeper into space you look, the further back in time you see. This means that we can never actually see what the universe looks like right now. We can only see what it looked like in the past. Those distant galaxies we observe might look completely different today. They might have collided with other galaxies, formed new stars, or had their stars burn out. But we won't know what they look like now for billions of years, when the light showing their current state finally reaches us. This creates a strange philosophical puzzle. What does now even mean on cosmic scales? There's no universal present moment. The concept of simultaneous events breaks down across vast distances. Einstein's theory of relativity tells us that time itself is relative, depending on motion and gravity. Two observers moving at different speeds will disagree about whether two distant events happened at the same time. The universe doesn't have a single timeline that everyone agrees on. Instead, every observer has their own perspective on when things happen. Let's talk about something equally mind-bending, the particle horizon. This is different from the observable universe. The particle horizon represents the maximum distance from which light could have reached us since the Big Bang, without accounting for the expansion of space. It's about 46.5 billion light-years away in every direction. Beyond that distance, there hasn't been enough time for light to reach us, even in principle. Those regions are causally disconnected from us. Nothing that happens there can affect us, and nothing we do can affect them. They exist in a separate bubble of causality, but here's the weird part. Because the universe is expanding, some regions that we can see now will eventually become causally disconnected from us. They're receding from us so fast due to cosmic expansion that light leaving them now will never reach us. We're watching them slip beyond the cosmic horizon forever. In the far future, if any civilizations still exist, they'll have a very different view of the universe than we do. They'll see fewer galaxies, and they'll have less evidence about the Big Bang and the early universe. Future astronomers might not even be able to figure out that the universe had a beginning. We're lucky to live in an era where we can still see the evidence of our cosmic origins. We can observe the cosmic microwave background, measure the expansion of space, and peer back to when the first galaxies were forming. We're living during a golden age of cosmology, when the universe is old enough for intelligent life to arise, but young enough that we can still study its history. Now let's consider something called the cosmological principle. This is the assumption that the universe looks roughly the same in all directions and from all locations. No matter where you are in the universe, if you look out far enough, you should see approximately the same distribution of galaxies, the same cosmic web structure, the same average density of matter. The universe has no center and no edge. Every point can be considered the center from its own perspective. This might seem strange. If the universe is expanding, doesn't that mean everything is expanding from a central point? Shouldn't we be able to look around and see where the Big Bang happened? The answer is no, because the Big Bang didn't happen at a point in space. It happened everywhere simultaneously. Space itself came into existence with the Big Bang and has been expanding ever since. Every point in space today was at the same location at the moment of the Big Bang. The entire universe was compressed into an infinitesimally small region, and then space expanded, carrying everything apart. Here's an analogy that might help. Imagine an infinite grid of dots on a rubber sheet. Now imagine the rubber sheet stretches uniformly in all directions. Every dot moves away from every other dot, but there's no central point that everything is moving away from. Each dot can consider itself the center, with all other dots moving away from it. That's what cosmic expansion is like. Galaxies aren't moving through space away from a central point. Space itself is expanding, carrying galaxies along with it. This expansion has profound implications. For one thing, it means the universe can expand faster than light without violating the speed limit imposed by relativity. The speed of light is the maximum speed at which anything can move through space, but there's no limit to how fast space itself can expand. In fact, the most distant galaxies we can see are currently receding from us at speeds faster than light due to the expansion of space between us and them. This sounds impossible, but it's perfectly consistent with relativity. They're not moving faster than light through their local space. Instead, the space between us and them is expanding so rapidly that the distance increases faster than light could traverse it. This also means there are galaxies we will never be able to reach, even if we could travel at the speed of light. They're too far away, and space is expanding too fast. Even a beam of light leaving Earth right now heading toward those distant galaxies will never reach them. The space between us is expanding faster than the light can cross it. It's like trying to walk forward on a treadmill that's moving backward faster than you can walk. You're moving forward relative to the treadmill, but you're still going backward relative to the room. Those galaxies exist beyond what's called the cosmic event horizon, and they're forever beyond our reach. Think about what that means. There are potentially trillions of galaxies that we could observe right now, but we can never visit, never communicate with, never affect in any way. They're real, they exist, but they're permanently separated from us by the expansion of space. If intelligent civilizations exist in those galaxies, we'll never meet them. We'll never share knowledge with them or learn from them. The universe is not just incomprehensibly large in space, it's also structured in such a way that most of it is forever inaccessible to us. But let's not get too depressed about that. Even the portion of the universe we can potentially explore is absurdly vast. Our own galaxy contains 400 billion stars. If we could somehow build starships and colonize the galaxy, it would take millions of years, even at a significant fraction of light speed. We haven't even left our own solar system yet, unless you count the Voyager probes, which are barely scratching the edge. We're nowhere close to becoming an interstellar species, let alone an intergalactic one. Some scientists have proposed ideas for how future civilizations might travel between stars. Generation ships, massive vessels where multiple generations would live and die during the journey to distant star systems. Suspended animation, freezing colonists and waking them when they arrive. Or perhaps some kind of breakthrough physics we haven't discovered yet, like wormholes or warp drives that could shortcut through space. These ideas remain purely theoretical for now. We don't know if they're possible, and we certainly don't have the technology to attempt them. There's also the question of whether we should attempt interstellar colonization, even if we could. Every star system might be home to its own unique chemistry, potentially even its own life. Would we have the right to colonize those systems and potentially disrupt or destroy whatever exists there? These are profound ethical questions that future generations will have to grapple with. For now, we're confined to Earth, this tiny blue marble suspended in an ocean of darkness. But that doesn't mean we can't explore the universe from here. Our telescopes allow us to visit distant worlds with our eyes and our minds, even if we can't go there physically. Every photon that enters our telescopes is a messenger from across space and time, carrying information about distant realms. When you understand what you're looking at, astronomy becomes a form of time travel and exploration that's available to anyone with access to a telescope or even just their naked eyes on a clear night. Speaking of exploration, let's discuss what we've learned about the early universe. The first few 100,000 years after the Big Bang are particularly fascinating and mysterious. During this period, the universe was so hot that matter existed as a plasma soup of protons, neutrons, electrons, and photons. This phase is sometimes called the photon epoch or the radiation-dominated era. The universe was opaque because photons couldn't travel freely. They constantly scattered off the charged particles in the plasma. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen and helium atoms. This event is called recombination. Even though the particles weren't actually combining again, it was the first time they formed atoms. With neutral atoms forming, photons could suddenly travel freely through space. The universe became transparent. This is the moment that created the cosmic microwave background radiation we observe today. But before recombination, there was an even more mysterious period called the Dark Ages. After the CMB was released, the universe contained mostly neutral hydrogen gas. There were no stars yet, no galaxies, nothing producing visible light. The universe was literally dark, illuminated only by the fading glow of the Big Bang itself, which was rapidly redshifting into infrared and then microwave wavelengths. This dark age lasted for about 100 million years. Then something extraordinary happened. Gravity began pulling the hydrogen gas together into denser clumps. These clumps continued collapsing until they became hot and dense enough in their cores to ignite nuclear fusion. The first stars were born. These were unlike any stars we see today. They were massive, perhaps hundreds of times more massive than our Sun, and they burned incredibly hot and bright. They were made almost entirely of hydrogen and helium because heavier elements didn't exist yet. Astronomers call these population 3 stars, and despite decades of searching, we've never directly observed one. They all died billions of years ago. These first stars didn't live long. Massive stars burn through their fuel quickly, sometimes in just a few million years. When they exhausted their hydrogen fuel, they exploded as supernovae, the first such explosions in cosmic history. These explosions created the first heavy elements: carbon, oxygen, nitrogen, iron, and many others. They scattered these elements throughout space, enriching the cosmic gas. The next generation of stars that formed included these heavy elements in their composition, making them slightly more like the stars we see today. This period, when the first stars ignited, is called the cosmic dawn, and it fundamentally changed the universe. The intense ultraviolet radiation from these first stars began breaking apart, or ionizing, the neutral hydrogen atoms in the surrounding gas. This process is called ionization, and it gradually transformed the universe from neutral to ionized over several hundred million years. By about 1 billion years after the Big Bang, ionization was complete, and the universe looked more like it does today, filled with shining stars and galaxies. Scientists are intensely interested in studying this cosmic dawn period because it represents such a crucial transition in cosmic history. That's one of the primary missions of the James Webb Space Telescope. Webb is specifically designed to see the infrared light from these early stars and galaxies. Because of cosmic expansion, the visible light they emitted has been stretched into infrared wavelengths. Webb can detect that light and show us what the universe looked like during its first few 100 million years. Some of Webb's discoveries have been genuinely surprising. As I mentioned earlier, some galaxies appear more massive and mature than our theories predicted they should be at such early times. One possibility is that our models of galaxy formation need revision. Perhaps galaxies can grow faster than we thought under certain conditions. Another possibility, and this is where those dark stars come in, is that some of these bright objects aren't galaxies at all, but rather individual supermassive stars powered by dark matter. If dark matter particles can annihilate each other, releasing energy, that energy could theoretically power a star far larger and brighter than any normal fusion-powered star. These dark stars, if they exist, could grow to tens of thousands or even millions of times the mass of our Sun. They would be so bright that they might look like entire galaxies from our perspective. Scientists are working to determine whether certain Webb observations match the predictions for dark stars. If confirmed, it would be revolutionary. We'd finally have direct observational evidence of dark matter doing something other than exerting gravitational pull. We'd see it actually powering objects interacting with normal matter in a detectable way. But whether these objects turn out to be dark stars or just surprisingly mature galaxies, one thing is certain. The early universe was far more dynamic and active than we imagined. Stars and galaxies emerged faster, grew larger more quickly, and began their cosmic evolution earlier than standard models predicted. Every new observation from Webb is refining our understanding and sometimes forcing us to rethink fundamental assumptions. Let's shift gears and talk about black holes because they represent another aspect of the universe's incomprehensible scale. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. They're created when massive stars collapse at the end of their lives or when enormous amounts of matter accumulate in small regions. Einstein's general relativity predicts their existence, and we now have overwhelming observational evidence that they're real. Stellar mass black holes formed from collapsed stars typically have masses between about 5 and a few dozen times the mass of the Sun. They're small, maybe 10 to 100 miles across. But don't let that fool you. The gravity near a black hole is so extreme that it warps space and time in ways that seem impossible. If you fell toward a black hole, from an outside observer's perspective, you would appear to slow down as you approach the event horizon, the boundary beyond which escape is impossible. You'd appear to freeze in time, never quite crossing the event horizon. But from your perspective, you'd cross the event horizon and continue falling toward the singularity at the center, where all the mass is compressed into an infinitesimally small point. The experience of falling into a black hole would be bizarre beyond description. As you fell, tidal forces would stretch you vertically and compress you horizontally, a process scientists cheerfully call spaghettification. Your feet, being closer to the singularity than your head, would experience stronger gravity. The difference in gravitational pull between your head and feet would literally stretch you like taffy. Near a stellar mass black hole, this would kill you long before you crossed the event horizon. Near a supermassive black hole, however, the event horizon is so large that tidal forces at that boundary would be relatively mild. You could cross the event horizon and survive for a while, falling deeper into the black hole's interior. What happens inside a black hole remains one of physics' greatest mysteries. General relativity predicts a singularity, a point of infinite density where the laws of physics break down. But most physicists believe this is a sign that general relativity is incomplete, not a description of reality. We need a theory of quantum gravity combining general relativity with quantum mechanics to understand what really happens at the center of a black hole. We don't have that theory yet, though many physicists are working on it. Then there are supermassive black holes, monsters with millions or billions of times the Sun's mass. Nearly every large galaxy has one at its center, including our Milky Way. The black hole at our galaxy's heart, Sagittarius A star, has a mass of about 4.3 million suns. It's been relatively quiet lately, not actively consuming much material, but it hasn't always been that way. Evidence suggests it was much more active in the past, potentially devouring stars and gas clouds. Some supermassive black holes are incredibly active, surrounded by swirling disks of material called accretion disks. As matter spirals into the black hole, Friction heats it to millions of degrees, causing it to emit intense radiation across the electromagnetic spectrum. These active galactic nuclei can outshine their entire host galaxy, pumping out more energy than billions of stars combined. Some eject massive jets of particles and energy perpendicular to the accretion disk, shooting out at nearly the speed of light and extending for thousands of light years. These jets are some of the most energetic phenomena in the universe. The largest known black holes are truly incomprehensible. TON 618, a black hole powering a distant quasar, has an estimated mass of 66 billion times that of our Sun. Phoenix A, another supermassive black hole, might be even larger, with estimates suggesting a mass up to 100 billion solar masses. These objects are so massive that their event horizons stretch for hundreds of billions of miles, larger than our entire solar system. If you replaced our Sun with one of these monsters, its event horizon would extend beyond Neptune's orbit. How do black holes get so massive? That's still an active area of research. They probably start from seed black holes in the early universe, perhaps formed from the first generation of massive stars. Then they grow by consuming gas, dust, and occasionally entire stars. They can also merge with other black holes. When two galaxies collide, their central supermassive black holes eventually spiral together and merge, creating an even larger black hole. This merger releases gravitational waves, ripples in space-time itself. We've detected these gravitational waves using instruments like LIGO and Virgo. In 2015, LIGO made the first direct detection of gravitational waves from two merging black holes, confirming a major prediction of Einstein's general relativity and opening an entirely new way of observing the universe. Instead of using light, we can now use gravity itself to detect cosmic events. Gravitational wave astronomy is still in its infancy, but it's already revealing phenomena we never knew existed. One of the most exciting prospects is detecting gravitational waves from the early universe itself. During the first fraction of a second after the Big Bang, violent processes might have created gravitational waves that are still propagating through space. Detecting these primordial gravitational waves would give us information about the universe at times and energies we can't access any other way. It would be like having a window into the moment of creation itself. Black holes also raise fascinating questions about information and entropy. According to quantum mechanics, information cannot be destroyed. But what happens to information when something falls into a black hole? Does it disappear forever, violating quantum mechanics? Or is it somehow preserved? Stephen Hawking spent much of his career grappling with this black hole information paradox. In his later years, he proposed that information might be encoded in the event horizon itself, preserved in subtle correlations in the Hawking radiation that black holes slowly emit. The paradox isn't fully resolved, and it remains one of the deepest problems in theoretical physics. Black holes might also be connected to the fundamental nature of space and time. Some theories suggest that our three-dimensional universe might actually be a holographic projection from information encoded on a two-dimensional surface, somewhat like a hologram. The mathematics describing black holes supports this holographic principle. If true, it would mean that reality as we experience it with three dimensions of space is actually an emergent property of something more fundamental, operating in fewer dimensions. The universe might be, in a very real sense, a cosmic hologram. These ideas push the boundaries of what we consider possible or even comprehensible. They take us far beyond everyday experience into realms where intuition completely breaks down. And that's exactly the point. The universe doesn't care about human intuition. It operates according to rules that often seem bizarre or impossible from our limited perspective. Our job as curious beings is to follow the evidence wherever it leads, even when it takes us to conclusions that seem absurd. Let's talk about something else that demonstrates the strange nature of cosmic scale, the speed of light as a cosmic speed limit. Light travels at approximately 186,000 miles per second. That sounds incredibly fast, and it is by human standards. Light can circle the Earth 7.5 times in 1 second. It can reach the Moon in about 1.3 seconds. It seems instantaneous to us in everyday life because the distances we deal with are so small, but on cosmic scales, the speed of light is frustratingly slow. It takes light over 8 minutes to travel from the Sun to Earth. That means if the Sun suddenly vanished, we wouldn't know for 8 minutes. We'd continue seeing it in the sky, continue feeling its warmth, completely unaware that it was already gone. When it finally disappeared from view, we'd also suddenly feel the gravitational effect of its disappearance. Interestingly, gravitational changes also propagate at the speed of light, so we'd lose the Sun's gravity at the same moment we lost its light. It takes light 4.2 years to reach us from Proxima Centauri, our nearest stellar neighbor. If you wanted to have a conversation with someone living on a planet around that star, assuming they exist, there would be an 8.4-year delay between question and answer. You'd be a different person by the time you got a response. Children born on the day you asked a question would be in elementary school by the time the answer arrived. For galaxies millions or billions of light years away, the light travel time becomes absurd. The Andromeda Galaxy is 2.5 million light years away. When you look at it, you're seeing it as it was 2.5 million years ago, long before humans existed. The galaxy you see in the sky doesn't exist anymore, not in that form. It's evolved, changed, formed new stars, lost old ones. But you're seeing ancient history, frozen in the photons that have been traveling through space for eons to reach your eyes. This creates what scientists call the look-back time. The farther away you look, the farther back in time you see. Astronomers use this to study cosmic history. By observing galaxies at different distances, they can see how galaxies have evolved over billions of years. It's like having a photo album of the universe at different ages. Nearby galaxies show us what galaxies look like in the relatively recent past. Distant galaxies show us what they looked like billions of years ago when the universe was young. The most distant galaxies we've observed are over 13 billion light years away. We're seeing them as they were just a few 100 million years after the Big Bang. These galaxies are young, small, and actively forming stars. They look nothing like the mature spiral and elliptical galaxies we see nearby. By comparing galaxies at different distances, astronomers can piece together the story of how galaxies form, grow, and evolve over cosmic time. But here's something that really puts the speed of light in perspective. If you could travel at light speed, which you can't because you have mass, it would still take you 100,000 years to cross our galaxy. It would take you 2.5 million years to reach Andromeda. It would take you over 13 billion years to reach the most distant galaxies we can observe. Even at the fastest speed the universe allows, the cosmos is so vast that crossing it would take longer than the current age of the universe. This has profound implications for the possibility of contact with alien civilizations. Even if intelligent life exists around nearby stars, communication would be incredibly slow. A simple back-and-forth exchange could take decades. Sending a probe to visit them would take centuries or millennia using any technology we can currently imagine. Unless someone discovers a way to circumvent the speed of light limit, perhaps through wormholes or some other exotic physics, interstellar communication and travel will remain painfully slow. Some scientists have speculated about advanced civilizations that might have spread across their entire galaxy over millions of years. If a civilization achieved interstellar travel and sent out colony ships that traveled at even a small fraction of light speed, those colonies could eventually send out their own colony ships. Over millions of years, a single civilization could theoretically colonize an entire galaxy, creating a vast network of worlds connected by slow but steady travel and communication. The fact that we don't see evidence of such a galactic civilization is sometimes called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If intelligent life is common in the galaxy, and if even a small fraction of those civilizations achieve interstellar travel, then over the billions of years the galaxy has existed, someone should have colonized everything by now. The fact that we don't see evidence of this suggests either that intelligent life is incredibly rare, or that something prevents civilizations from spreading across the galaxy, or that we're not recognizing the signs of their presence. There are many proposed solutions to the Fermi paradox. Maybe intelligent life is rare, emerging only under very specific conditions. Maybe advanced civilizations tend to destroy themselves before achieving interstellar travel. Maybe interstellar travel is just too difficult and civilizations remain confined to their home star systems. Maybe advanced civilizations exist, but choose not to reveal themselves to primitive species like us. Maybe they've transcended physical form and exist in ways we can't detect. Or maybe, and this is perhaps the most unsettling possibility, we're actually alone in the universe, the only conscious observers in a vast cosmic wilderness. We simply don't know. The sample size for intelligent civilizations is exactly one, us. We can't draw statistical conclusions from a single data point. The search for extraterrestrial intelligence continues through projects like SETI, which scans the skies for artificial radio signals, and through the study of exoplanets, searching for biosignatures in their atmospheres. So far, we've found nothing conclusive, but the search has barely begun. We've only examined a tiny fraction of the stars in our galaxy, and we've only recently developed the technology to study exoplanet atmospheres. In 2025, scientists announced potential biosignatures in the atmospheres of several exoplanets observed by JWST and other telescopes. These are gases that could be produced by biological processes, though they could also have non-biological explanations. The data is intriguing but not conclusive. We need more observations, better instruments, and careful analysis before we can claim to have found evidence of life beyond Earth, but we're getting closer. Within the next few decades, we might actually answer the question of whether life exists elsewhere in the universe. Imagine what that discovery would mean. If we found even simple microbial life on another world, it would prove that life isn't unique to Earth. It would suggest that the universe might be teeming with life, from bacteria to potentially intelligent civilizations. It would be the most profound discovery in human history, fundamentally changing our understanding of our place in the cosmos. Conversely, if we searched thoroughly and found nothing, that would also be significant. It would suggest that life is incredibly rare, that Earth is special, that we might be precious and unique in ways we can barely comprehend. Both possibilities, that life is common or that we're alone, are equally profound and equally awe-inspiring in different ways. Let's return to thinking about scale in a different way. We've talked about distances, but what about quantities? How many stars exist? How many planets? How many atoms? The numbers become so large they lose all meaning, but let's try anyway. The observable universe contains an estimated 2 trillion galaxies. Each galaxy contains anywhere from millions to trillions of stars. Let's be conservative and say the average galaxy has 100 billion stars. That gives us approximately 200 billion trillion stars, or 2 times 10 to the power of 23 stars. Now let's think about atoms. A typical star like our Sun contains about 10 to the power of 57 atoms. Multiply that by the number of stars and you get roughly 2 times 10 to the power of 80 atoms in all the stars in the observable universe. But stars only contain a small fraction of all the atoms. Most atoms are in interstellar gas, dust, and planets. When you account for all the matter, you get approximately 10 to the power of 80 particles in the observable universe. 10 to the power of 80. That's a 1 followed by 80 zeros. To put that in perspective, there are only about 10 to the power of 18 grains of sand on all of Earth's beaches. There are more atoms in a single grain of sand than there are grains of sand on Earth. And there are more atoms in the observable universe than there are atoms in 1,000,000 trillion Earths. The scale of matter in the universe is incomprehensible. But wait, there's more. Those 10 to the power of 80 particles are just the normal matter we can see and touch. That's only about 5% of the universe's total energy content. About 27% is dark matter, which we can't see but can detect through its gravitational effects. And about 68% is dark energy, the mysterious force driving the accelerated expansion of the universe. So the matter we can see, everything made of atoms, all the stars and planets and nebulae, represents just a tiny fraction of what actually exists. This is humbling beyond words. We've spent centuries studying the universe, building ever more sophisticated instruments, developing complex theories, and training brilliant minds. And after all that effort, we've discovered that we only understand 5% of what's out there. The remaining 95% is composed of substances we can barely detect and don't fully understand. It's like trying to understand a novel when 95% of the words are invisible. You can see the basic plot, but most of the story remains hidden. Dark matter reveals itself through gravitational effects. Galaxies rotate faster than they should based on the visible matter alone. Something invisible is providing additional gravity, holding the galaxies together. Galaxy clusters show similar anomalies. When scientists map the distribution of mass in clusters using gravitational lensing, where massive objects bend light passing near them, they find far more mass than can be accounted for by visible matter. That invisible mass is dark matter. Scientists have proposed various candidates for what dark matter might be. WIMPs, or weakly interacting massive particles, are hypothetical particles that interact with normal matter only through gravity and possibly the weak nuclear force. Axions are another candidate, extremely light particles that could exist in enormous quantities. Or dark matter could be primordial black holes created in the early universe before stars existed. Despite decades of searching, we haven't directly detected dark matter particles yet, but the search continues with increasingly sensitive experiments. Dark energy is even more mysterious. In the late 1990s, astronomers studying distant supernovae discovered that the universe's expansion is accelerating. This was completely unexpected. Gravity should slow down expansion, pulling everything back together. But instead, expansion is speeding up, as if some repulsive force is pushing everything apart. Scientists call this force dark energy, though we have no idea what it actually is. One possibility is that dark energy is the energy of empty space itself, sometimes called vacuum energy, or the cosmological constant. Quantum field theory predicts that even empty space should contain energy due to quantum fluctuations. But when physicists try to calculate how much energy empty space should have, they get an answer that's about 10 to the power of 120 times larger than what we observe. This has been called the worst prediction in the history of physics. Something is clearly wrong with our understanding, but we don't know what. Another possibility is that dark energy isn't constant but changes over time. This hypothetical form of dark energy is called quintessence, and it could be associated with a new field permeating space. Or maybe dark energy is a sign that Einstein's general relativity breaks down on cosmic scales, and we need a modified theory of gravity. Various proposals exist, but none have been confirmed. The nature of dark energy determines the ultimate fate of the universe. If dark energy remains constant, the universe will continue expanding forever, eventually reaching a state of maximum entropy called heat death. All stars will burn out, all black holes will evaporate, and the universe will become a cold, dark, uniform sea of particles spread across infinite space. This will take incomprehensibly long, far longer than the current age of the universe, but it seems to be where we're headed. If dark energy is increasing over time, a more dramatic fate awaits. The expansion could accelerate so much that it eventually tears apart galaxies, then solar systems, then planets, then atoms themselves. This scenario is called the Big Rip, and it would happen in a finite time, maybe tens of billions of years from now. As the expansion accelerates, the forces holding matter together would eventually be overcome, and everything would be shredded into fundamental particles. If dark energy decreases or becomes negative, expansion could slow down, stop, and reverse. The universe would begin contracting, galaxies would crash together, and everything would collapse back into a hot, dense state similar to the Big Bang. This is called the Big Crunch. Some theories suggest this could lead to a big bounce, where the universe is reborn in a new Big Bang, creating a cyclic cosmology where universes are born, expand, contract, and are reborn eternally. Which fate awaits us? We don't know. Our observations suggest the expansion is accelerating and will continue doing so, leading to eternal expansion and heat death. But dark energy is so poorly understood that we can't be certain. Recent observations suggesting dark energy might be weakening have added new uncertainty to the picture. The ultimate fate of the universe remains an open question, one that future observations and theories will hopefully answer. Let's bring this back to something more immediate and personal. We've talked about the incomprehensible scale of the universe, the vast distances, the enormous quantities, the mysterious dark matter and dark energy. But what does this all mean for you, for us, for humanity? Why should you care about cosmic scale when you have immediate concerns like paying bills, maintaining relationships, and getting through each day? Here's why it matters. Understanding our place in the cosmos gives us perspective. When you realize that you're standing on a planet orbiting a star that's one of hundreds of billions in a galaxy that's one of trillions in the observable universe, it puts your problems in perspective. That argument you had, that embarrassment you experienced, that failure that haunts you, none of it matters on a cosmic scale. The universe is vast and ancient and will continue long after you're gone. This might sound depressing, but it's actually liberating. If nothing we do matters cosmically, then we're free to decide what matters to us personally. We can create our own meaning, our own purpose. You're not cosmically significant, and that's okay. You're locally significant. You matter to the people around you. Your actions have consequences for your community, your society, your species. That's enough. In fact, it's everything. At the same time, understanding cosmic scale should fill you with wonder and humility. You're made of atoms forged in stars billions of years ago. You're a temporary arrangement of matter that has somehow become conscious, able to contemplate its own existence. You're the universe examining itself, a way for the cosmos to know itself. That's profound, that's beautiful, that's worth celebrating. The fact that we can understand any of this is remarkable. A few hundred years ago, we thought the Earth was the center of everything. We had no idea about other galaxies, no concept of the Big Bang, no understanding of cosmic expansion. In just a few centuries, we've gone from complete ignorance to a detailed understanding of cosmic history spanning nearly 14 billion years. We've mapped the universe from the quantum scale to the cosmic scale. We've discovered the fundamental laws governing matter, energy, space, and time. Yes, we still have enormous gaps in our knowledge. We don't understand dark matter or dark energy. We don't have a theory of quantum gravity. We don't know if we're alone in the universe. We don't know why the universe exists at all. But the fact that we can even ask these questions, that we can recognize the limits of our knowledge, is extraordinary. No other species on Earth, as far as we know, can contemplate cosmology. That ability might be unique to us in our entire cosmic neighborhood. This makes knowledge precious. Every observation, every measurement, every theoretical insight represents hard-won understanding extracted from an indifferent universe. Scientists have dedicated their lives to pushing back the boundaries of ignorance. They've built telescopes and particle accelerators, developed mathematical frameworks, and spent years analyzing data, all to understand reality a little bit better. That work deserves respect and celebration. It also means we have a responsibility. We're the universe's way of knowing itself, at least in this small corner of space. If we destroy ourselves through war, environmental catastrophe, or some other self-inflicted disaster, we'll be snuffing out something precious and possibly rare. We don't know if intelligent life is common or rare in the universe, but we know it exists here. We have an obligation to preserve it, to nurture it, to give it the chance to flourish and grow. Looking up at the night sky should inspire more than just awe. It should inspire action. It should motivate us to solve our problems, to overcome our divisions, to work together as a species. The universe is vast and mostly empty, but it has produced islands of complexity where matter has organized itself into stars, planets, and living beings. Earth is one of those islands, and as far as we know, it might be the only place in the visible universe where life has become conscious enough to understand what it is and where it came from. That makes Earth extraordinarily precious. It's not just our home, it might be the universe's only chance, in this region of space at least, to produce something capable of understanding itself. We've been given an incredible gift: consciousness, intelligence, curiosity. We can look up at the stars and comprehend what we're seeing. We can trace our origins back to the Big Bang. We can predict the future evolution of the cosmos. No other species we know of can do this. But with that gift comes responsibility. We're capable of both creation and destruction on scales that would have been unimaginable to our ancestors. We've split the atom and walked on the moon. We've eradicated diseases and connected the entire world through technology. We've also developed weapons capable of destroying civilization, polluted our atmosphere and oceans, and driven countless species to extinction. The same intelligence that allows us to understand the cosmos also gives us the power to destroy the only known cradle of life in the universe. The next few centuries will be critical for humanity. We face existential challenges: climate change, nuclear weapons, artificial intelligence, biotechnology, resource depletion. How we handle these challenges will determine whether we survive and flourish or collapse and disappear. From a cosmic perspective, it doesn't matter. The universe will continue with or without us. Stars will keep burning, galaxies will keep evolving, space will keep expanding. But from our perspective, from the perspective of every person who has ever lived or will ever live, it matters tremendously. If we succeed, if we navigate these challenges and create a sustainable, peaceful, technologically advanced civilization, the possibilities are extraordinary. We could spread throughout the solar system, establishing colonies on Mars, the Moon, and the moons of the outer planets. We could eventually venture to other star systems, becoming an interstellar species. Over millions of years, we or our descendants could explore the galaxy, maybe even beyond. We could encounter other forms of life, other civilizations. We could learn things about the universe that we can't even imagine right now. Even if we never leave our solar system, even if interstellar travel proves impossible, we could still create something beautiful and lasting. We could build a civilization that lasts for millions or billions of years, producing art, music, literature, science, and philosophy beyond anything we can currently conceive. We could become wise stewards of our planet, preserving its ecosystems and allowing life to continue evolving. We could decode the deepest mysteries of physics, consciousness, and existence itself. Or we could fail. We could destroy ourselves in a nuclear war. We could render Earth uninhabitable through environmental destruction. We could create an artificial intelligence that surpasses us and decides we're unnecessary. We could succumb to a pandemic, natural or engineered. We could simply stagnate, losing our curiosity and drive, becoming a dying civilization that fades into obscurity. The universe won't care which path we take, but we should care. Every person alive today is part of this story, part of this critical moment in human history. Understanding cosmic scale should give you perspective on these challenges. Yes, they're serious. Yes, they're urgent, but they're also solvable. We've solved difficult problems before. We've overcome seemingly impossible obstacles. We've survived ice ages, plagues, wars, and disasters. We're remarkably resilient and creative when we need to be. The same intelligence that discovered quantum mechanics and mapped the cosmos can surely figure out how to power our civilization without destroying our atmosphere, how to feed everyone without depleting our soils and oceans, how to resolve conflicts without resorting to violence. The key is perspective. When you understand how vast the universe is, how ancient, how complex, you realize that our current problems, while serious, are also temporary and local. Climate change is a huge challenge, but it's happening on one planet, orbiting one star in one galaxy. It's not a cosmic catastrophe, it's a problem we created, and we can solve it if we choose to. Nuclear weapons are terrifying, but they only threaten one species on one world. We could eliminate them if we had the collective will to do so. Understanding cosmic scale also teaches humility. We're not the center of the universe. Earth doesn't occupy a special position in space. Humans aren't the inevitable endpoint of evolution. We're one species among millions, living on one planet among potentially billions, orbiting one star among hundreds of billions, in one galaxy among trillions. We're small, temporary, and fragile, but we're also rare, possibly unique, and certainly precious. That combination of insignificance and significance should shape how we see ourselves and how we act. It should make us less arrogant and more collaborative. If we're this small in the cosmic scheme of things, why do we fight over arbitrary borders? Why do we hoard resources while others starve? Why do we cling to ideologies and identities that divide us when we're all equally insignificant from a cosmic perspective? We're all humans, all made of the same stardust, all standing on the same tiny planet in the vastness of space. Our similarities vastly outweigh our differences. At the same time, understanding our cosmic context should inspire us to preserve and celebrate what makes us special. We can create art, music, and literature. We can love, laugh, and dream. We can contemplate infinity and probe the nature of reality. We can ask why the universe exists and what it means to be conscious. These abilities might be common in the universe, or they might be incredibly rare. Either way, they're precious and worth nurturing. So what should you do with this knowledge? How should understanding cosmic scale change your life? There's no single answer, but here are some thoughts. First, maintain perspective. When things seem overwhelming, remember that you're a temporary arrangement of atoms on a small planet in a vast universe. Your problems are real and matter to you, but they're also small in the grand scheme of things. This can be comforting when you're stressed or anxious. Second, embrace curiosity. The universe is endlessly fascinating, full of mysteries and wonders. Keep learning, keep asking questions, keep exploring. You don't need a PhD in physics to appreciate the cosmos. Just look up at the night sky occasionally, learn the names of a few constellations, follow astronomy news, watch documentaries, read books. Let yourself feel wonder at the scale and complexity of existence. Third, recognize your connection to the cosmos. You're not separate from the universe, you're part of it. The atoms in your body were forged in stars. The energy powering your cells comes from the sun. You're a product of billions of years of cosmic and biological evolution. Understanding this connection can provide a sense of belonging and meaning that transcends individual circumstances. Fourth, act responsibly. You're part of something larger than yourself, something ancient and vast. Your actions have consequences not just for you, but for the broader community of life on Earth, and potentially for the future of humanity. Make choices that reflect this understanding. Be kind, be curious, be thoughtful. Contribute something positive to the world. Help preserve the precious gift of life and consciousness that the universe has produced. Finally, don't let the scale of the universe make you feel powerless or nihilistic. Yes, you're cosmically insignificant. Yes, the universe will continue regardless of what you do. But you're locally significant. You affect the people around you. Your choices matter to your community, your society, your species. You have the power to make things better or worse within your sphere of influence. Use that power wisely. The universe is 13.8 billion years old and 93 billion light-years across. It contains 2 trillion galaxies, each with billions or trillions of stars. The distances are incomprehensible, the timescales unimaginable, the quantities beyond human comprehension. And yet here you are, a conscious observer capable of understanding all of this. You can hold the entire cosmos in your mind, at least conceptually. That's miraculous. In a universe this vast and ancient, the fact that you exist at all is extraordinary. The fact that you can think, feel, and understand is remarkable. The fact that you can look up at the stars and comprehend what you're seeing is profound. You're the universe contemplating itself, a brief flicker of awareness in an ocean of unconscious matter and energy. Make the most of it. Look up at the night sky tonight if you can. Find a dark place away from city lights if possible. Let your eyes adjust. You'll see thousands of stars, each one a sun like ours, many probably orbiting planet. You'll see the band of the Milky Way stretching across the sky, the combined light of billions of distant stars in our galaxy. If you're lucky, you might see Andromeda, a faint smudge of light that's actually an entire galaxy of trillions of stars 2.5 million light-years away. Remember that the light entering your eyes has been traveling for years, decades, centuries, or millennia. You're seeing these objects as they were in the past. You're literally looking back in time. Every photon is a messenger from across space and time, carrying information about distant worlds and ancient events. And remember that you're made of the same stuff as those stars. You're stardust that has somehow become aware of its cosmic origins. The universe is vast beyond comprehension, ancient beyond imagination, complex beyond description. But it's also your home, your origin, and possibly your future. You're a small part of something incomprehensibly large, but you're also a crucial part. Without observers like you, the universe would just exist without knowing it exists. Consciousness, wherever it arises, is the universe's way of experiencing itself, of reflecting on its own existence. That's the scale of the universe. It's not just about distances and quantities. It's about perspective, meaning, and purpose. It's about understanding where you came from, where you are, and where you might be going. It's about recognizing both your insignificance and your significance, your temporariness and your preciousness. It's about feeling awe at the cosmos while also recognizing your place within it. You are here, now, alive and aware in a universe that is mostly dark, cold, and empty. That's an incredible privilege and an extraordinary responsibility. Are you into the light speed topic? If so, this next video at the left side of the screen is perfect for you. In this video, we explore why the speed of light is the absolute cosmic speed limit and what Richard Feynman did to uncover the terrifying truth of space-time and causality. See you there.